Hello. Let's talk about fork-join parallelism. In some parallel applications, multiple work items can be processed in parallel. However, dependencies between those work items, or the order in which they must be processed, do not allow us to just enumerate them with a loop. To parallelize such algorithms, we may use the fork-join model of parallel execution, which puts in effect a tree of tasks. In this model, tasks may spawn children parallel tasks and synchronize between them. For example, parallel recursion is easier expressed with the fork-join model than with the parallel for loop.
To express the fork-join, OpenMP provides the functionality of tasks. To start a task, the programmer uses the statement pragma OMP task. The code in the scope of this pragma becomes an independent task, which is scheduled for execution in one of the OpenMP threads. To wait for all tasks spawned from the current scope, use the statement pragma OMP taskwait. Good parallel algorithms will have at least as many tasks as there are available threads, preferably much more. For example, on an Intel Xeon Phi coprocessor with 240 threads, we should aim to have hundreds or thousands of tasks. This will not oversubscribe the system. OpenMP will make sure that no more threads are executing at a given time than there are available in the system. This code is a generic program that implements parallel recursive divide-and-conquer algorithm in OpenMP. We'll recursively split the problem into two subproblems until the subproblem size is small enough for processing in one thread. Execution begins in the initial thread. Then we start a parallel region and immediately use pragma OMP single, which restricts execution to a single thread and puts the rest of the threads in standby. From that single thread, we call the top function of the recursive tree. Inside the function, we will have a branch that continues or stops recursion depending on how deep we have recursed. If the problem is still big enough, we split it into two subproblems, but each subproblem is placed into an OpenMP task, which begin execution in different OpenMP thread. If the subproblem is small enough for serial execution, we have reached the deepest levels of the task tree, so we execute these subproblems serially. Notice that we used a new clause in this task pragma firstprivate. This clause is similar to the clause private, which we saw in the previous episode. It creates a private copy of the variable args1 or args2 for each of the tasks. However, in addition, firstprivate initializes that variable inside the task to the value that we had outside of the scope of the task.
Parallel loops and tasks in OpenMP give us access to parallel algorithms in shared memory that can express a great variety of computing tasks. Now it is time to discuss topics that are necessary for coordinating how multiple threads work toward a common goal without compromising each other's results. The topics are thread synchronization and parallel reduction. We'll begin discussing those topics in the next episode.